Ah, spooky. There it goes. Okay, great. All right, I don't know what's going on there. Hi, everybody. I had an interesting conversation after lecture last time, which was I miss writing on the board because then it's easier to take notes and then I can think harder and I don't lose my chain of thought as much. Any thoughts on this? Anybody want to give their opinions on whether it's harder to maintain attention with slides versus writing? Yeah. Okay. Board, you can kind of back look. Other thoughts? Just as I'm feeling it out. I'm not changing for you now, but yeah. Okay. Writing on the slides? Tell me more. Oh, that's nicer because I don't have to escape. Yeah, I should do that. I have an iPad. That's my daughter's with the pen, so maybe I'll try that out. Other thoughts? Slides writing. Yeah. Oh, you want vacancy so you can write on my slides? Yeah. You mean? Okay, that's fair. All right, I'll consider it. Any other thoughts? Yeah. Yes. Right. Yeah. Certainly more density here. Less interaction, I think, is what you said. Okay, cool. Good to know. All right. Well, let's talk about random variables today. Someone also mentioned they really like having questions to do in the middle, which helps them keep their train of thought. This is a lecture which was entirely pre-recorded last semester, so there's not as many questions as I wanted. I'm like right on the razor's edge, like many of you in terms of what I'm busy with, but I also had a sick child last night, so that ate a lot of the day. So let's do it. Let's talk about random variables. I'm going to talk informally about where they even come from before I introduce them formally. Let's suppose that we're flipping a coin 4 times, and we'll say x is the number of heads that we will see in that process. So what is x? What is this thing? Well, I can tell you just informally that it's some number between 0 and 4. I don't know which of those numbers, but it's definitely one of them. And I can start to do kind of like algebra with this fuzzy thing. So I could say, well, what is x plus 3? Well, I know it can't be 0 anymore. I just know it's some value between 3 and 7. Okay. What's x minus x? 0 is just 0. I don't know what x actually will be, but I know that whatever it is, if I subtract it from itself, it'll be 0. If I say, what's x squared, what's that going to be? What could it be, I guess? Could it be 0?
It could be 0, 1,
yeah.
4, 9, or 16.
Exactly. So it's one of those values, 0, 1, 4, 9, or 16. That's the notion that a random variable is trying to capture. Okay? And we're going to try and find, what's the right definition to capture this thing? I'm actually just going to give it away. But that's the goal. Random variables are supposed to capture this feeling so that we can reason about these kind of fuzzy variables, these random variables. Okay? Let's say we actually have 2 random variables, x and y, just to start feeling this out. Today we're going to focus on one random variable at a time. But for the sake of setting our course for the future, let's say x is the number of heads and y is the number of tails. What is x plus y? 4, right? So we know that it's 4. So even though each of those separate quantities is random, added together they're 4. It kind of feels like quantum physics, right? There's some fuzziness, but if you look at it just the right angle, you make a measurement, the right kind of measurements, there's an exact value. What's x minus y? It's a little harder to think about.
It could be anything from -4 to 4.
Right, somewhere from -4 to 4, although you can't have odd numbers. That'd be weird, but these are the sets you can have. So you could have no heads and 4 tails. You could have 1 heads and 3 tails and so forth. Okay? So again, x minus y, it makes sense. I can talk about it as a thing, right? It's like some number from one of these sets, and if we start thinking about probabilities, we could say how relatively likely each one is, and we'll get there. But that's the notion that a random variable is supposed to convey. Okay, another one, to get even weirder. Let's say I take 100 students' homework, so you all come in with your homework, and then I pick them up, and then I hand them back to you. So I get all of them, and I hand you one, you one, you one. And x is the number of students who get their own homework. So what's x going to be? Okay, so, well, what could it be? Could be 0 to 100. Okay. Are there any numbers that feel like it definitely couldn't be if you pay really close attention, if you're clever? Yeah? 99 wouldn't make any sense. You can't have everybody get their homework back except one person. That doesn't make logical sense. Is x more likely to be 1 or 3? I don't know. What's your gut feeling? If you had to guess. Who thinks 1 is more likely without having studied this? Okay, 3. Okay, no idea, everybody else. Okay, it turns out to be much more likely to be 1, and we'll be deconstructing this distribution later. Okay, kind of interesting, though, that 1's more common than 3. Okay, what's x on average? What do you think? Yeah? 0? Okay, close. Turns out to be 1. So if all of you give me a thing and I hand them back randomly, on average, one of you will get the thing back, which is pretty cool. And we're going to see that in a couple different ways in this class, some easier than others. And I think it's a nice puzzle that one can solve with the tools we're going to be developing. Okay, so let's start working our way towards what a random variable is formally. I think you have a sense of what they are in a fuzzy, informal manner. And I'm also going to plug in my laptop. So let's say we flip a coin 4 times, and x is the number of heads that we see. Well, since the value of x depends on the result of an experiment, I can't give you a specific value, of course, as we've just been saying, but I could enumerate everything possible. So there's 4 tails up top. There's HTTT, THTT, TTHT, and TTTH. What I can think about if I look at this table is that here's my original kind of like, it's the sample space. It's all the sample points that exist. And then over here, I have basically the number that goes with each of these. So why does the number 2 go with tails, heads, heads, tails? Because that's the number of heads we see. That's how we defined it. What is x? Like looking at this table. Like, what is it? It's a number of heads, yeah? What kind of mathematical object is it? It's not a distribution. It's something you know. So what does x seem to be taking as inputs? Yeah? Go ahead. Yeah, it's taking omega. So it's like for each omega, you get a particular number. So I can think about x as what? Yeah? Close. Not quite. Nope, not heads. I'll give you a hint. There's inputs and outputs. Functions. It's a function. And is it really a function? Right? Yeah, sure. Like each object goes to some other value. It's not like sometimes heads goes to 4 and sometimes it goes to 3. It is actually a function. So curiously, even though this notion of a random variable that we've been playing with in an informal way feels like a fuzzy number, actually the definition in probability is that it is a function. Okay, so random variables are functions, is what we'll say. Okay? So given a sample space, a random variable is a function that takes outcomes and gives you back a real number. Now, I didn't give you real numbers here. I gave you integers, the counts of the number of heads. But in principle, it could be anything. Like it could be the fraction of heads, in which case this would be 0. This would be 1/4, 1/2, 3/4, and 1. Okay? There's no restrictions on like a probability function that they need to add to 1 or anything. There's none of that. All it is a function that takes outcomes, and it gives you some number. And that number is maybe, in this case, it's a summary of what all the coin flips were. But in principle, all kinds of other things are possible. Okay? Any questions about this? So it's a little funny that the thing I was saying earlier is like, oh, well, what's x plus y? We know it's 4. Okay, what is the thing I'm adding? Well, it's actually like it's functions. That's what I'm working with. When I'm talking about a random variable, formally they're functions that take samples and give you back an arbitrary number. And I'll give you other weirder functions on coin flips. Any questions about this? Okay, all right. Another example of a random variable. Let's imagine rolling 2 dice, 1 gold die and 1 blue die. And let's say x is a random variable, in other words, a function that takes those pairs of numbers and gives you back another number. In this case, it'll be their sum. So 1 plus 1 is going to be 2. And so this function here takes pairs of numbers and gives you back their sum. It's not a very exciting function, but you can imagine filling this whole table out. And so we can think of this random variable x. It's a function whose domain is the set of all pairs or tuples of integers I, j, where I and j are between 1 and 6. And the range of the function is 2 through 12. Okay? So that's another random variable. Okay? Another weirder one that we're going to see later today is a sample space which is all possible coin flips that consist of tails followed by heads. And it could be 0 tails. That's possible. Okay? So the sample space is heads, tails, heads, tails, 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 heads, tails, tails, heads, not necessarily in that order. 4 tails, then heads, 5 tails, then heads, and so forth. And so this right here is what our sample space is. And then all x does is it counts the number of flips until we get our first heads, and we start at 1, not at 0. Okay? So the domain of this random variable is infinitely large, right? This is Hilbert's hotel type territory. It's any number of tails followed by heads at the end, and the range is going to be the natural numbers not including 0. And this actually, it turns out to be an important random variable that we'll be talking about in a little bit, called a geometric random variable. Good for assessing the odds of winning it big on random, say, out-of-the-money options trades. Yeah. Yes. Yeah, includes both 4, 6 and 6, 4. Yeah. So I'm calling them ordered tuples. Yeah. And if it wasn't that, I would have only included like the upper triangle or the upper triangle of it, if I only wanted one particular order. But in this particular case, I said the sample space is all, I guess, pairs of die rolls considering order. I didn't actually explicitly say that, but that's what I intended. Okay. And you can get more exotic with these, but this is what a random variable is. You have a sample space. You have a function that takes each sample and gives you back a number. Good. All right, let's make it more concrete by playing around with some more specific random variables. And let me also tell you what a distribution of a random variable is. So here again are some coin flips. We know this example well. And I've come up with a very strange random variable, which counts the longest run. Okay? What do I mean by a run? Well, it's a sequence of flips that are all the same. This is just, you wouldn't really see this random variable ever. I just picked it to be extremely arbitrary. So for example, if I have these 4 coin flips here, heads, tails, 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 this random variable C gives me back 3, because the longest run is 3 tails at the end. This one right here, heads, heads, tails, heads, gives me back 2. And so this function will take each of these 16 different possible flips, and it'll give you back some number, which is somewhere between 1 and 4. Okay? So this random variable, again, it just takes each of these items and spreads them out. So let's consider the following. Okay, so this right here, I'm going to be very careful about talking through this. Let's consider this set. What is this set? The way you should read what I've written on the slide, and it also appears in the notes this way, it's the set of all omega in the sample space, and this colon you should read as such that, and it's that the random variable maps that sample to 4. So question for you, is that set, do you call that an event on omega? What do you think? I think maybe, hold on a sec. Okay, yeah, oh, gave it away, okay. So is that set an event on omega? I said yes, implicitly there. So why is that set an event? What's an event? You guys remember, like, how do we formally say what an event is in a sample space? Yeah? Just a subset. So any set that contains 0 or more of these items in the sample space will be an event. Okay, so this is an event, right? An event is just a subset of the sample space. And so when I read this thing out here, what is the set of omega such that C of omega is 4? That gives me exactly these 2 sample points. And those 2 sample points, of course, comprise some event. Here it is. Okay, so this event has 2 items in it, 2 sample points. Okay? All right. What is the probability of this event? Because remember, events have probabilities. Okay, so how do I get the probability of this event? Well, we're just going to add up the probability of the individual samples. So if the coin is fair, it's going to be just 2/16. That's the probability of this event. Okay, it's awkward notation right here to write all this stuff, and we're going to have a more compact notation soon. But the idea is that given a random variable, you have all of these different samples that map to some particular value, in this case 4, right? Because this is the longest run is 4. And then an event will be all of the things that map to 4. Okay. Any questions about this? Okay. All right, so I find this notation unwieldy, and so usually what we do is we'll just write this set as C equals 4. All right? And that's what we'll see throughout the notes, and just a simpler way of expressing this exact idea. Instead of saying the omegas in the sample space such that C of omega equals 4, we just say C equals 4. okay, casually. But it would be fair to say that tails, 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 tails is a member of the set C equals 4, and so is head, heads, head, heads. Okay, so it's a little funky notation for a set because it has an equal sign in its name. But if you don't stress too much about that, it works out okay. And so anytime we're saying the probability of C equals 4, we're really saying the probability of the set of all omega in the sample space such that C omega is 4. And this is just a shorthand. Okay. Now you could have other notations. You might see these elsewhere. You could say, oh, well, it's all of the items that if we, I have seen this occasionally, a pre-image here, that this is one way to express all the items that map to 4, or you could say C sub 4. We're not going to use those. They're not in the notes, so I'm just going to stick with saying C equals 4. Okay. All right. More terminology, not that it's necessarily the most exciting thing, but I want to think about this question. So is it the case that a random variable partitions a sample space? Okay, so what was that again? Again, I still want to try and reinforce our terminology that we don't necessarily think about when we're doing homeworks or discussions. So in lecture 16, I said that, paraphrasing a bit, the sample space is partitioned into a bunch of events if the union of all those events is the entire sample space, and if the intersection of any pair of events is disjoint. Okay, or it's null. Okay? Is this claim true or false? I'll give you a minute to think about this. Feel free to discuss amongst your buddies or enemies. Except it's the wrong thing. One sec. Here you go. I'll show you the secret magic. So you can't answer yet because it's the wrong question. Let's go to my URL shortener. Sometimes you have to build your own URL shortener because that's better. This is lecture 18. Okay, I think it should work now. Let's find out. Oh, except you can't see it anymore. Okay, good. Okay. All right, I'm going to wait just a bit more. Yeah. Any random variable. Yeah, a random variable. Okay. All right, so the correct answer is true, and maybe there's a little fuzziness earlier that might have made that not obvious. We were at 75% correct. So the reason it's true is that for every sample point in the sample space, so every combination of heads and tails, if you'd like, the random variable maps you to exactly one event. It's never the case that there's two possibilities. If you get heads, heads, tails, heads, it's definitely going to give you 3 if you're counting heads. It's definitely going to give you 2 if it's counting the longest run. It's definitely going to give you 1 if you're counting tails. Whatever it is, the random variable is some deterministic function of each sample that gives you some real number, whatever it is. One thing I don't know that I said out loud is that our random variable has to be defined over the entire sample space, so some of you might have been worried about that. Yeah? Yes, exactly. You can think of it as a bijection if you'd like. Yeah. Okay, so you can go... precisely. Okay. So we can consider the sample space of, let's say, 4 coin flips using this random variable C, which counts the longest run. It takes our sample space and it partitions it into these 4 events. And notice that the intersection of any pair of these events is empty. And that if I combine them all together, I get the entire sample space. So what's this event? Give me a name for this thing. C equals 1, exactly. This one's what? C equals 3, this one's C equals 2, and this one's C equals 4. And these events are each different sizes and therefore have different probabilities, but the entire space, assuming I didn't mess up when I was drawing these little dragony looking things, they partition the space. Okay? Yeah.
When it's always be the longest run, or like can we define different things?
Yeah, so in our case, I define C as looking at the longest run. But another equally valid random variable would be number of heads. And in that case, the 4 heads by itself would be its own event. And then you'd have all the 3 heads possibilities, yeah. So for every random variable you define, you get a different partition of the sample space. Yeah?
Would it ever be possible to define a random variable that has some sort of overlap, or like by definition that just cannot happen?
It could have some overlap, meaning there's like some...
No longer by definition.
Yeah, I don't think I would call it a random variable anymore. It's an interesting question. Is there a way to generalize where there's some natural reason that some samples have sort of a superposition? I don't know. I don't think so. Yeah. Yeah. Where some samples aren't covered? Or, I mean, I guess you could, but we always partition the entire space, yeah.
Come up with a random variable that's like the number of coin flips with at least one head.
Right, number of coin flips with at least one head.
Because then there would be overlap.
Well, but the thing is, the function's supposed to take individual sample points and tell you which number goes with that sample point. Right? Does that make sense? So the number of coin flips with at least one head is just, I think it's not a random variable because it doesn't tell you for each sample point what number goes with that. Does that make sense? Like what you're describing is like a question, like how many of them have at least one heads, but it's not a random variable because a random variable is always for every sample point, how many, or what property, what real number goes with that sample point. Makes sense, yeah.
How is partitioning by junction? Because like where's the one-to-one mapping?
Oh, because you can't go the other way. I might have misspoken in there. Sorry. Yeah. All right. Okay. So moving on. Pairs of dice. Let x be a random variable that sums the result of 2 dice. Again, x in this case would partition the sample space of pairs of dice into events. And again, the reason that happens is because for every possible pair of dice, we get a particular number. Here are all the events. Here are their names. I gave some of them. Okay? So again, you take your sample space, you partition it, and you're in great shape. Okay. All right. Okay. The next thing I want to talk about is the distribution of a random variable, which is going to seem a little dry for a moment. So the distribution of a random variable is given in the notes with this expression here. It's the set of all values in the range of x and their probabilities. That is, we have here, each of these pairs is a specific number. Like here I have a. And we have the range of x. So in this particular case, the range was 1, 2, 3, and 4. And what I'm doing is for each possible value in this range, so this is 1, 1, this is 2, this is 1, this is 2, this is 3, and this is 4. I'm going to give a pair, which is the value from the range and the probability that goes with that specific possibility. So the distribution of this random variable is this set of these 4 pairs. So why is it 1, 2/16? That's because the number a, this is the number of runs basically here that have the max length of a run is 1, and there's 2 of those. Here there are 8 of these, there are 4 of these, and there are 2 of those. Any questions about this here? Okay. All right. And so the distribution, you can always think of it as exactly this, right? You just enumerate all the things a random variable can give you, every value in the range of the random variable, and then you enumerate the probabilities of each of those values in the range. If we also do it with, for example, this sum of 2 6-sided dice, the distribution is a little messier, right? Now we have all the values 2 through 12, and we have this little staircase where we go up from 136 to 236 to 336 to 436 to 536 to 636 and so forth. Now, this is sort of an awkward way of writing out a distribution. So often what you'll see is instead it's given as a table or a plot. But the fundamental mathematical object, as we describe it in the notes, is this set of pairs of numbers from the range and their probabilities. But this is, after all of that effort and all this formalization, this is basically a table which if I had told you nothing, if I'd started the lecture from that table, you would understand what it is, but we wouldn't have that machinery of precisely what a random variable is underlying it, right? So here I have a is 2, a is 3, a is 4, and so forth. random variables will be discrete for most of the class, but we will have 1 week where they become continuous. And this is the one part of the class where calculus is necessary to really know what's going on, but for the very small number of you who have not done calculus, you will still be able to sort of meander your way through. But yeah. Okay. We can also show this distribution as a plot if you'd like. It's the same thing as this table, of course. This is just a nice plot showing the possibilities of getting each output for my random variable function here. Okay. All right. Now, I do want to note that summing random variables is a funny operation. The thing you get back is very different. So the original distribution for rolling a 6-sided die is just flat. It's 1/6 for all of the 6 die rolls. But once you add 2 of them together, you get something totally different right here. So 136, 236, and so forth. So not only do you get a number of possibilities, it's a little bit weird, right? Because this case I had 6 possibilities. This one I had 11. Like that feels a little like strange at first. Like it's not obvious just glancing at it that you should go from 6 to 11. And also that you get this staircase is not super obvious. So when you add 2 random variables, something interesting happens. And where you might start with a nice random variable, the sum may be not so nice. You don't stay, like the distribution can be dramatically different in shape. And we'll see this later. Any questions about that? Yes, there is, by the way, a way to take distributions and mechanically compute this new thing. But it requires an operation we won't really talk about in our class. But you'll know it if you've done signals and systems called convolution. Okay. Let's talk about another distribution. So we saw this pair of die rolls. Let's talk about tossing 100 coins. So if I have 100 coins and I toss them, that's a fun thing to do. My kids once raided that little fountain by Memorial Glade and took all the coins home. So if you're wondering where the coins went, they're in my daughter's Ziploc bag. And if they were to take those coins, which number in approximately 100, and threw them, you could count the number of heads you get back, and you get back some number. So you might get back, for example, 100 if they were all heads. So what is the distribution of x? What does it look like? Okay. Well, the probability of x equals a, and remember that is the probability of the event where we take all the omegas in the entire sample space, and we run them through x, and we find all the ones that equal a. That's just going to be, naturally, the number of outcomes with a heads over the number of different coin flips. This is just the same old stuff we're doing before. Nothing new, but now we have this notion of random variables layered on top. So that's going to be 100 choose a. That's a number of different ways that we can pick our heads. And that's going to be divided by the total number of different coin flips, 2 to the 100. And so if I look at this right here, I can plot this function. So I pick a particular a, say 50, plug it into this equation, I get some number. Okay? And you'll notice that I get this nice sigmoidal curve. Now earlier I mentioned this notion that if you add 2 random variables, their combination is not going to resemble the originals. But as we'll see later, if you keep adding a lot of random variables together that are independent, you will observe this interesting phenomenon that even if the original, so if the random variables are all the same distribution, we'll say for now, and you add them all together, lots and lots of them, you end up getting this characteristic shape that you're very familiar with. It looks more Gaussian or normal, or like exam distributions kind of, right? Maybe. Okay. That's a little for later, okay? Next one for you. Okay, got one for you to think about, and this I'm going to give you a couple minutes to think about. Let's suppose we take a homework from 3 students, and we randomly give them back to other students. So you can think about each of these as an example, like 1, 2, 3. Think about this sample point as I took the 3 students' homework, and I gave back 1 to 1, 2 to 2, and 3 to 3. And we'll say x is the number of students who get their own homework. What's the distribution of x? And I'm going to give you like 2 full minutes. Go for it. So what is the distribution is the first thing you have to remember. 20 more seconds. Okay. This distribution, it's a set of whats? If we're going to be real formal, what is a distribution? It's a set of whats? How many things are in the set? I mean, yeah, I guess you could say 3 or 6. I guess either one's reasonable. Well, wait, 3, yes. 3, yes, it must be 3. Okay, so it's a set of 3 things, and what are they? Tuples, yeah, that are values and their probabilities. Okay, so the way I think about it, that's weird. We're misaligned. Curse you. Okay. One moment. Why is there an X? What does the X mean? Oh, okay. Aha, never mind. Everything's fine. X is the name for the random variable. Okay. All right, so what is X going to be? So for this one right here, how many do we get back? How many do we correct here? It's 3. All right, here, we got one of them right. Okay, how about this one? 1, yep, this one? 0, 0, and 1. So the distribution looks like that. So the part where I paused for a moment was when someone said there's 3 values. I guess you could call it either 0, or so you could either call it 3 or 4 things in the distribution. It's a matter of whether or not you want to consider 2 as in this range. I don't know. I don't have a good answer for that. You could either call it the range includes 2, and it has a probability of 0, or the range doesn't include it. I actually don't. I think either definition seems perfectly reasonable. Okay. All right. Any questions about that? So as you can see here, the most common answer is 1. And if you take this distribution and you consider all the permutations for, say, 100, 1 will still be the most common. And as, again, we'll see later, the expectation will also be 1, so that no matter how many students you have, the average number you expect to get back that are your own is 1. But that's for the future. Yeah?
Wouldn't the second to last value, for the 100 coins, the 99 also was another option? Similarly, would that always not be an option?
Oh, for flipping 100 coins?
That was just an
Oh, for giving back 100 homeworks? Yeah, for giving back 100 homeworks, 99 would also be probability 0.
So, is that a theorem or something that,
I guess you could call it a small theorem for specifically giving back homeworks, yes. Does it tie into something else? Probably, but I don't know else. Yeah. It's kind of a mini version of the pigeonhole, right? Yeah. Okay. All right. Okay, let's talk about expectations then. So we have this handy notion of the average of something. So if I pick a random student from CS 70 and I say X is their grade on the first midterm, what are some interesting questions we might ask about X? Well, we might ask, what's my grade? Okay, sure. But you might also ask, what's the distribution of X? Or what is the average of X? We'll call that the expectation of X. Or we might talk about the standard deviation of X. These are all things we could ask. But we're going to focus on the expectation here as our second thing. And this third thing will come in another later lecture. Okay. So I'm going to do a little experiment, and we're going to flip some coins. This is pretty fun to do. Okay, so here we go. Coin flipping simulator. I'm flipping some coins over time. And as I'm flipping coins, I am counting, the total number of heads across all the flips. Okay, so here we go. Oh, sorry, one more time. 4 coins. So can we do just one? Yeah, there we go. So current flip. Our flip was heads, heads, tails, tails. And what we're showing in the simulation is we're counting the number of heads. Okay, so we're going to keep going. All right, so as we're flipping, we're seeing how many times we flipped 4 coins did we get that many heads. Okay, so we can just keep going. We can flip, 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 flip. I heard a weird sound. Okay, there we go. Okay. And we can run the simulation for a long time. And we can ask ourselves, what is the average number we get? So when I did this little experiment, I got an average of 2.11. Okay, and I also saw this little, I guess I'll call this an empirical distribution of flips. And every time I do it, I'll get something slightly different. But you'll notice the average number of heads I get it's around 2. Okay. what we want to do is formally discuss this. If we have a random variable and we were to keep, oh, that's interesting. That's pretty good there. If we kept doing this over and over, flipping over and over, what's a relationship between a random experiment and what we would expect to happen theoretically? And what is this thing right here? Like this quantity here that seems to be about 2. That's what we're going to go for, okay? So when I did an experiment done before class, when I only did 20 flips, the average number of heads I got was 1.7. 1, 2, and 3 were the most common, occurring 25% of the time. But when I just did the live experiment and I had many more flips, I had a different outcome, right? When I did 150 flips just on my own before class, I had 1.99. 2 was the most common value, occurring 40% of the time, and so forth. And what I'll observe is that if this is actually modeling reality, that if I flip more and more and more and more coins, the histogram is going to look increasingly like the distribution, right? I mean, the distribution is supposed to reflect the probability that things happen. So if I keep doing the experiment, I should eventually get numbers that look very similar. Now let's suppose we knew the exact distribution for x. Like we know that it is, the distributions like you computed earlier. How do we compute the average? What's that going to look like? Okay. Basically, you can think of that as that's the average value that you'd get if the simulation, like if you let the simulation run forever, what it would converge to. Okay. So expectation formally is given with a formula that's natural but a little peculiar at first. Which is the expected value of a random variable x. And here I'm going to insist on using the brackets as opposed to the parentheses, because even my wild heart can't bear the idea of parentheses for expectation. It's going to be the sum over all of the values in the range of the random variable. Okay, so you take each of those values and you multiply them by the probability that that value pops up. Okay, so why does this make sense? Well, let's consider the case of flipping 4 coins. So in this particular case, if we want to know what should the average be, when we compute this expectation, it's simply going to be each of these numbers here, a, times the probability you get this value. So 0 times 1/16 plus 1 times 4/16 plus 2 times 6/16 plus 3 times 4/16 plus 4 times 1/16. And I'll get more of an argument for why this makes sense, but what you get if you actually compute this sum is 2. Okay, I'm going to come back to that, but for the sake of my sanity, let's talk about some example distributions. How about that? Okay. So what I failed at, right? Let me just explain to you what I failed at, and I will think about it further. Was justifying this expectation formula by trying to relate it to experimental averages. So that's where I failed you. What I can promise you that this is true. For some reason, this particular argument in this moment of totally cooked brain just didn't happen. All right, let's continue on, and I will try and rescue you. Okay. So let's talk about different random variables. Bernoulli random variables in particular is where we're going to start. So let's suppose here I have this random variable. This is the first and simplest random variable. So a Bernoulli random variable has this distribution that there's 2 possible values that can happen, 0 or 1. You can think of it as a coin flip, that 0 is tails and 1 is heads, and p is the probability of getting heads. Okay. So this probability, x equals a, this is the whole distribution. These are the 2 possible values in the range of the random variable, and these are the probabilities. So for example, let's suppose we flip a coin that comes up 75% of the time heads. We'll say that x is 1 if the coin comes up heads, and 0 if it comes up tails. Okay? That would be an example of such a thing. In this case, we'd say x is distributed as a Bernoulli random variable with p equals 0.75. Or in writing, often you'll just see that x, and we'll use this tilde symbol to indicate that this is a random variable that is a Bernoulli random variable. And since a Bernoulli random variable is characterized entirely by one parameter, you can put it in here in parentheses. Okay? So that's just shorthand for saying x is distributed as a Bernoulli random variable with p equal to 0.75. Okay. These are not the most exciting random variables, but they are the cornerstone of many other things that we'll do, including binomial random variables, Poisson random variables, and geometric random variables. Okay. So let's suppose x is a Bernoulli random variable with parameter 0.5. What's the expected value? Okay, well, we're just going to shuffle off into shake off the existential dread that came from that part of lecture. And we're going to think about what is the expected value. Okay, well, the expected value is just going to be 0 times the probability that x is 0 plus 1 times the probability that x is 1. So what is this going to be? So it's 0 times, so probability x equals 0 is 1 minus p. In this particular case, let's say it's 0.5. And let's say the probability of x equals 1 is 0.5, because that's the parameter we have up here. Then the expected value is just going to be 0 times this plus 1 times this, and you get 0.5. In other words, if you have a coin that has a 50% chance of getting heads, and heads is 1, the average you expect is half. Okay, that's the short version. Okay. Now, I do note that the expected value of a random variable can be something out of its range, right? So an expected value takes a bunch of samples and maps them to real numbers, and this expected value is some number that it can never be, but that's still okay. That's allowed. Okay. In general, if we're talking about a Bernoulli random variable with probability value p, the expected value is just going to be p. So 0 times 1 minus p plus 1 times p. It's just the same exact math, except I put in p in place of 0.5. Okay, happy with that? All right, great. How about 2 Bernoulli random variables? Now, we haven't said what precisely an independent random variable is yet, but let's suppose we have y equals x1 plus x2. What's the distribution of y, and what's the expected value of y? Okay. Is it also going to be a Bernoulli random variable if we add 2 of them? My first question for you. What do you think? So you take 2 Bernoullis and add them, do you get a Bernoulli back? Who thinks yes? No? Okay, give me an argument. Why can it not be a Bernoulli? What's the range of a Bernoulli random variable? 0 and 1. What's the range of the sum of 2 Bernoulli random variables? 0, 1, and 2. So it's not Bernoulli anymore. Okay, so it's something else. Okay, what is its distribution? Well, it's going to be like this. There's going to be a p squared chance you got 2 heads, let's call it. You have a 2p times 1 minus p chance that you got 1 heads. Okay, there's 2 ways to get it. And then there's 1 minus p squared chance that you had 2 tails. Okay, yeah. Yeah, I think this one's fine. Okay. What's the expected value of y? Okay. Well, we're just going to take each of these things. We're going to say it's 0 times p squared plus 1 times 2p times 1 minus p plus 0 times 1 minus p squared. Okay, because that's just the range. Type each of these. P of y. Oh, yeah, this should be a y. Yes, thank you. This should be a y. This is where being able to write on the slide would be good. Okay. All right. That was the thing you spotted. Okay. All right. We just multiply that stuff out. So 2p squared, right here we got 1 times 2p times 1 minus p. Okay, that's 2p. Minus 2p squared, if you multiply this out, and this one's just 0. So we end up with 2p. Okay, so in other words, we note in this particular case, and we'll see in the next lecture this is generally true, that the expectation of the sum of these two things is just the sum of the separate expectations. Okay. All right. How about binomial? So binomial random variable is another very popular one. This models the number of heads if we flip in coins that come up with probability p. Okay. So let's try out a specific example. Let's say we're flipping 5 coins which have some particular probability p of coming up heads. So for example, the probability of heads, heads, tails, heads, tails. We done so much of this in the counting lecture. That's going to be p times 1 minus p times p times 1 minus p. P cubed times 1 minus p squared. Okay, what about tail, tail, head, head, head? Okay, the probability of this specific single outcome is, again, p cubed times 1 minus p squared. How about the probability that x equals 3? What's that going to be? Okay. And I have here a thing for you to work out. And this is just a repeat of the counting lecture, but I think it's good practice. I'll see if you guys are willing to answer this one since it involves typing. Okay. wait for maybe 3 more. Okay, so it's the number of sequences with 3 heads times p cubed times 1 minus p squared. This is our usual idea, that we have a bunch of different possible ways of getting 3 heads, and each of them has this exact probability, and then we just need to how many of them are. We have 5 choose 3, which you could think of as picking the positions of those 3 heads. You can also have written this as 5 choose 2. That's also okay, because then you're picking the positions of the 2 tails. Okay? So that's the probability of this binomial of x equals 3, which is the probability of adding up all the probabilities of all the omegas that this random variable maps to 3. If I want to say to I, well, it's just the same pattern. I'm just going to replace the bottom of the choose with I. This is going to become I, and this is going to become, in this particular case, 5 minus I. And so why is this 5? And why is this 5? Because we're flipping 5 coins. Okay? And naturally, if we want to generalize to any number of coins, we're just going to replace this 5 with n. Okay, so that is the probability of getting any particular number of heads, and actually we've already done that. Homework 8 was a bunch of that. Previous lectures were a bunch of that. So this hopefully was well-worn territory for you. All right. So this right here is the binomial random variables distribution if we plot it to get a sense of what it looks like. And I'll observe that it is, of course, well, actually, here's a question. What's the relationship between this binomial random variable and a Bernoulli random variable? Yeah? Yeah, it's the sum of a bunch of Bernoullis. And so what started as a really simple random variable, you add them up, enough of them together, and you get this nice smooth shape. And now we'll see, I think, the ugly slide shortly. Okay. One thing you could do as an exercise in algebra, which I'm not going to do to you, certainly not a good idea in my brain right now, is you can verify that if you add this up over all possible n's, that you'll get 1. And we'll cover the expectation of a binomial random variable in the next lecture. You can do it using our normal sum, the one that I failed at deriving earlier. But that's a lot messier than using the nice approach we'll see in the next lecture. Okay. Here's my sort of not so nice slide, okay, because I kind of hacked this one together right before lecture, which is just showing what happens as you get different numbers of Bernoullis added together. So an initial single Bernoulli random variable looks like this. If I add 2 of them together, it looks like that. If I add 4 of them together, it looks like that, 16 like that, and so forth. And you see that it gets more and more bell curve shaped. And this is, again, something that is a generic feature that we'll see often with random variables. But that's what happens here. All right. Any questions about the Bernoulli or binomial connection or binomials in general? Okay, let's talk about geometric. Okay, we're doing a little bit of a grab bag today. This is a pretty popular one. This is I'm waiting for a bus, or I'm making random stock trades or whatever. And so I'm imagining a random experiment where I'm flipping a coin repeatedly, and it has a probability of heads equal to p until we get heads. And those flips are going to be totally independent. Okay, so it's not quite a good model for a bus, waiting for a bus. Why? I mean, like, because the bus, they're presumably driving out there. Like, if the bus has not come for a while, it's more likely to come soon. So maybe not. It's a crude model, I guess, of waiting for a bus. But it's definitely a good model for things that are totally independent. Okay? So x is the number of flips that we're going to make. And x is the number of flips until we get heads. And this distribution is called the geometric distribution. And it's going to be characterized by a single parameter p. So unlike a binomial where we had a specific number of flips, with a geometric, we're flipping until we get heads. That's the goal. So in the coin flipping example, what are the domain and range of this random variable? What's the domain? It's a function. What does it take? Thoughts? Hope I didn't lose you forever with that bad derivation. Yeah.
Is it just the result of our flips?
Yeah, sure. So what possible flips are there? Heads and tails. I want more precise, though. It's not any sequence, yeah?
The domain is basically, x can take on values from
Yep. But from 1 to infinity. Yeah. The range is 1 to infinity. What's the domain? Someone said flips earlier. That's right. But I want to be more specific. What kind of flips? Yeah? Everything's tails, but then it ends with a heads. So it has to be tails, tails, heads, tails, 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 heads, or just heads. So the domains, actually, we saw it earlier in the lecture. It's a sequence of potentially infinite numbers of tails followed by heads at the end. Okay? So you have 0 more tails followed by heads, and it's all the natural numbers other than 0. So what's the probability of x equals 1? What do you think? What's the probability you get a heads right off the bat? Well, it's p. Yeah, not half. If it was fair, it'd be half, yeah, but otherwise it's p. Okay? What's the probability that x equals I? What's that going to look like? Well, we already know the probability x equals 1 is p. What about x equals 2? Well, that's, you got tails, and then you got heads. So 1 minus p, then p. X equals 3 is 1 minus p squared times p. X equals I is 1 minus p times I to the minus 1 times p, just generalizing. And so that's going to be our distribution. For every possible value we have here, there's going to be this probability that we get that particular value. And of course, there's actually just one sample point in the sample space. So every sample point in the sample space goes with exactly one real number. There's only one way to get 4. Tails, 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 heads. Okay. All right. So let's verify that these probabilities actually sum to 1, right? I just said that that's the probability of getting any particular number of flips before you get heads. If we want to verify that these probabilities sum to 1, how does that go? Okay. So we want to sum up all of these probabilities all the way from 1, which is the smallest value, up to infinity. So how do I do that? Well, I notice that p over here, there's nothing to it, right? I'm just going to pull it out. It has no dependence on I. So now we're summing up 1 minus p to the I minus 1 from 1 to infinity. Here I'm going to use our little geometric series formula that if I have r to the n, if r is less than 1, this is going to be equal to 1. I don't actually have that condition here, but r should be less than 1. This is going to be 1 minus 1, 1 over 1 minus r. If I plug this in here, I get p over 1 minus 1 minus p. This p is the one over here. Okay, so all I've done here is just taken this right here and put it inside the minus sign. So just I took the 1 minus p and plugged it in for r here. That's p over p, which is 1. And that's good, because if the probability were something else, what would that mean? We made some terrible mistake, right? The probability of all the outcomes need to add to 1. Okay. Now geometric, actually questions about this? Okay. So this is just a little exercise in adding. This isn't critical. The other stuff's more important. So geometric random variables have this nice property that they're memoryless. Okay, so it basically means even if you've waited a long time, the chance of the event occurring soon isn't any better. This is the rebuttal of the gambler's fallacy. Who knows what the gambler's fallacy is? Yeah, what is it?
90% of gamblers quit before they win big.
90% of gamblers quit before they win big? That's the gambler's fallacy. Oh, I love it. That's funny. I hadn't heard that variant of the gambler's fallacy. So keep gambling, friends. That's the message of the class. The true gambler's fallacy is that if you've been losing a lot, a win is coming soon. All right. Yeah, so that's the, yeah. So basically, if you're playing roulette, I don't know if you've ever been to a casino, but they'll list like all the things that have happened lately. And they'll be like, wow, reds happened 10 times in a row. So it is not actually a good idea to walk up and bet on black at that point, because it is a memoryless process. Okay? So you're flipping a coin, and it came up 10 times in a row tails. The chance of heads isn't any better just because you had 10 tails. Okay? This is a little bit slightly counterintuitive, but maybe also exactly intuitive. Or if you're like, I don't know, buying way out of the money stock options over and over, and you keep losing, it doesn't mean you're going to win soon. So we want to show that these random variables are memoryless, that geometric random variables have this property. So in terms of probability, we can state this as we've already tossed a coin m times without getting ahead. The probability that we need n additional tosses is the same as if we hadn't tossed the coins at all. So you can pretend like I haven't done any of the experiment. That's what memorylessness means. You'll talk about this in discussion, but basically symbolically it means the following. The probability that I'm going to need so suppose I've already had to flip at least m times. Okay? The probability that I need to flip more, like n plus m times, more than n plus m times, is the same as if it hadn't flipped at all. Okay, so I could ignore this fact. It's like totally pointless. Like knowing that I flipped m doesn't affect what's going to happen in the future. So the probability that it's going to take, like let's say I flipped 100 times already, the probability that I need to flip like 10 plus 100, they need to flip 110 times, given that I've already flipped 100 times, is the same as the original probability that I just needed to flip more than 10. Okay, so how do I show that? Okay. So one thing I can do is just use definition 14.1 here to relate these two events. These are just events, right? And remember that any event in these, these are events like any other that we've done in class. Okay. So we say that this probability here, just using our usual definition 14.1, is that. I can write this out. What is the probability that x is greater than m? Okay, so there's something interesting going here. It's not obvious, but if I have a geometric random variable, why is the probability that x is greater than m equal to 1 minus p to the m? Anybody have a short argument for that? Yeah. Say again? Not the summation nation. I want something just more concise. Yeah.
The formula for p of x equals I, obviously removing the p because I get.
Well, I mean, you could start going back to that formula and adding a bunch of terms, but there's a more concise argument. Yeah. You haven't gotten heads yet. You've gotten, or even better, you've gotten tails m times. So the probability that x is greater than m is the probability that your first m flips are false, they're tails. So this right here, the chance that you had to flip, that your first m flips were wrong is 1 minus p to the m. Because the chance your first flip was wrong, so to speak, is 1 minus p. The chance that the first two was wrong is 1 minus p squared, and so forth. So if you want to know the probability that x is greater than some quantity for a geometric random variable, it has this simple expression that, yes, you can derive by summing a bunch of terms, but it's better just to think, okay, I've flipped tails that many times so far. Okay? Now, if I take this expression here and I divide it out, I, of course, will just get 1 minus p to the n. And that right there is just the probability of what? That x is greater than what? N, right. Okay, and that's what we were trying to show before. Now, there's a little bit of, I think the part that I don't know, I tried to do it by plugging 100 and 110 when I spoke out loud. This being the memorylessness property maybe is not totally obvious, but definitely reflect on this later. The rest is just algebra. Okay, so it doesn't matter that I did the first so many flips. They're irrelevant. It's memoryless. Okay. Here's another question. Let's suppose we have a coin where the probability of heads is 0.2. How many flips do you think we need to wait on average before we get our first heads? What's your gut feeling? Yeah? 5. Okay, you're right. Good. So it turns out that's true. The expected value of x is going to be, for a geometric random variable, 1 over p, but I'm going to wait until the next lecture to do that one. Okay, so we have to wait for 5 flips on average before we get heads. Okay. All right, we got one more today in our grab bag. And the reason it's kind of a grab bag is because we want you to get familiar with these kind of very different textured random variables, and then go into discussion, and then be able to solve some practical problems using them. And then in the next lecture, we'll be revisiting some properties, including linearity of expectation. And I will come back to this expectation proof that I just totally flamed out on in an embarrassing display of incompetence. All right, anyway, Poisson. So our last distribution is the Poisson distribution. And it's interesting because I'm going to talk about the relationship between each of these. A Bernoulli random variable is a single coin flip. The binomial is the sum of different coin flips. And the geometric random variable is a sequence of Bernoullis until you get something you want, until you get heads. Poisson is going to be also secretly under the hood a Bernoulli, but I'm not going to tell you the Bernoulli connection today exactly, but it has to do with sort of a limit of an infinite number of coin flips that are very unlikely to come up heads. But that's just like underneath under the rug for now. Okay. So Poisson for now is going to seem very different. Okay. Let's suppose we want to know, we have some radiation source that is in quasi-steady state, meaning it's not radiating so fast that it's going to stop emitting soon. It's emitting at a steady rate. And x is the number of emissions per unit time. The Poisson distribution is what you would use in probability to say how many emissions you expect to see. Okay? So the assumptions we make with a Poisson distribution is that the average number of emissions is going to be, let's say, lambda alpha particles per unit time. An alpha particle, it's helium. It's helium. It's helium for sure. But what's special about it? Tell me more about alpha. 4 protons, 2 neutrons. Is that? 2 protons, 2 neutrons. So the total atomic weight's, it's 4. Wow. You know, you get old and all these things you feel like you know are good. Like beta's an electron. I feel good about that. Gamma's light. But I forgot the number of protons. Now, actually, here's a question for you. Can you have, if it wouldn't be helium if you had 4 protons, could you have 2 protons and 4 neutrons? Would that just explode? Helium-6 exists? It's unstable. How unstable? Yeah. Does it emit beta particles or alpha particles? It'd be pretty funny if it just shot out. Anyway, pointless. Okay, I'm not going to go there. Okay, so helium-6 exists, and it's pretty unstable. We don't know how unstable. Not important. Okay, so lambda alpha particles, though, that's what we got. We got heliums coming out, 2 protons, 2 neutrons. We're also assuming that the emissions in disjoint time intervals are independent. In other words, if 2 particles were emitted in this interval 0 to 2, that tells us nothing about how many were emitted in this interval. Okay? And that's what I mean when I say that it's not like shedding radiation so fast that its rate is decaying over time. And so these intervals are totally disjoint. Okay? If these assumptions hold, and I'll come at it from a different angle that's less weird in the next lecture, but if these assumptions hold, we say that this random variable is Poisson with parameter lambda. And the distribution for a Poisson random variable is the probability of x equal to I is equal to this funny expression here. Lambda, that's the characterization of a Poisson random variable to the I, over I factorial, times e to the minus lambda. And for now, that's just a totally mysterious equation. And this is I equals 0, 1, 2, and so forth. Okay? So x tells you the number of emissions per unit time, and I'll give you an example in a moment. Okay? So we might say to ourselves, if we have a Poisson random variable that is 2 emissions per minute, what this random variable lets us do is it says, what's the probability of seeing 3 emissions in any given minute? Okay, that's the kind of question that this Poisson random variable very naturally lends itself to asking. So what we could do in this particular case is we literally just plug in the number 3. That's what this random variable means. So we'd say 2 to the third over 3 factorial times e to the minus 2. And again, I'm not telling you where this expression came from. It is just given to you by God, and in the next lecture, I will tell you more about where it came from. So we plug this in, we get 8/6 e to the minus 2, which is 18.04. So that's the probability of seeing 3 emissions in any given minute. Okay? Yeah?
Where did the lambda come from?
So the lambda is just, it's just in the same sense of where did the fairness of the coin come from, right? So you might say, where did P come from in a Bernoulli? So here it's just, that's just.
And what exactly is it supposed to represent?
It's the number, it's the average number of emissions per unit time in this radiation.
The average of x.
Sure, yeah. Yes, it is also the expectation of x, yeah.
What happens if x equals lambda? Shouldn't it equal like some special value?
If x equals lambda, so if x. Oh yeah, what does it work out to in some nice way? I don't know. I lack the brain cells to do this right now, apparently. Yeah. If it's some special, I don't know. I'll think about that. It's a good question. Okay. So where does this thing come from? Just very roughly as a preamble to the next lecture, it comes from the large N limit for binomial random variables. You can think of this as arising from an infinite number of Bernoulli trials over and over and over. And again, that's more next lecture for today. It's magic. As you brought up earlier, like what is lambda? I said it's the average number, or we said it's the expected value of this Poisson random variable, and that's by definition, right? We said it's the average number of events per unit time, so it makes sense. Like that's just what it was by definition. There's another nice property that we'll talk about in the next lecture, which is unlike Bernoulli's, where you add to Bernoulli's and you get an auto Bernoulli. Poisson random variables, if they're independent, if you add them together, you really do get, or in this case, you actually do get another Poisson. So the addition operation for 2 Poissons gives you back another Poisson that's just a sum of the, like it's a new Poisson whose average parameter here is just the sum of the original 2. Okay? And again, we're not equipped to prove that yet, and that's going to be in the next lecture. Okay, because I haven't talked about what independent random variables even are. All right. Question? Yeah.
Yeah, I was just wondering, like, for the Poisson random variable equation, let's say that we wanted to see, like, the probability of having 0 emissions per unit time.
Mm-hmm.
Is that possible? Because
That's a good question.
by 0.
Yeah.
So if we want to, like, what's the chances, like, per unit time nothing's actually happening? Can Poisson handle that, or?
Good question. Let me think about that a little again, my addled brain. 0 factorial is 1.
I forgot all that.
Okay, yeah, I think we're okay. Yeah, okay. Then we're in good shape. Yeah, it does tell you. Okay, yeah. Okay, all right. Another example, let's say we have 2 radiation sources then. One that we measure, or that we model as a Poisson with lambda 1 and the other with Poisson lambda 2. If the first one's 2 emissions a minute and the other one's 5 emissions per minute, what is the chance the total number of emissions is 4 emissions in a given minute? And again, I have to give these lambdas in some particular units. I said emissions per minute. And so I claim that the sum of 2 independent random variables that are Poisson are also Poisson. So the sum will just be you add these 2 different separate lambda 1 and lambda 2s. So if I want to know the answer to that, I'm just going to plug in, let's say I want to know the probability that the number of emissions is 4, then I'll get 9.1% in this case. So if my goal was what's the chance in a given unit interval that it's 4 emissions, it would be 9.1%. And that makes some sense. If I have 2 random sources that are firing off particles randomly, it makes sense that I should just be able to combine them like so. So it matches that intuition. And lastly, I have this other sort of funny argument here, which is about if the units don't match. I don't know if this is worth our time, but I decided to do it anyway. So let's suppose we model this as a Poisson random variable where we have lambda equals 2 emissions per minute, but we want to know the probability we get 100 emissions in an hour. So how does that work? Like, how do I square that? Well, in my case, I think, well, just convert our units. 2 emissions per minute is 120 emissions per hour. So I'll say that y is just going to be the same thing as x, our original random variable, but in units of emissions per hour. And so then y is going to be Poisson of 120. And in that particular case, if I wanted to plug in and know what's the chance to get 100 emissions an hour, it's just the same old formula, right? Now using our new parameter, 120, and we get some number, 0.68%. And the reason I bring this up is this is consistent with the idea of adding up many Poisson random variables, right? Because remember that each of the different intervals, that they're independent of each other. So an alternate way of thinking about this is that it's really just the sum of 60 independent random variables that are each Poisson. Okay, so converting units from minutes to hours is kind of like saying, okay, well, let's just treat it as 60 different Poisson random variables. Okay, in that case, then S is the sum. Okay, well, what's the sum going to be if we add up a bunch of Poisson random variables, 60 of them that have parameter 2, you get 120 here. And in this particular case, you'll get the same answer, 0.68%. Okay, so wrapping up, maybe this is mildly interesting. I don't know. I thought it was interesting last year when I was thinking about it, that unit conversion can be thought of as a sum of different random variables. Kind of fun. Okay, so to summarize here, today I told you what a random variable is. I felt pretty good about that. It's a function that maps outcomes to real numbers. Hopefully you feel really good about that. We saw many different distributions and some of their expectations. The thing, of course, that I failed at was explaining to you why the expectation formula makes sense in terms of my my little experiment. And so what I'm going to do is I'm going to send you a short video where I'm going to fix it, because that was quite embarrassing. All right, thank you, everybody. I hope you had a good time and that it was useful, despite my brain being mush today. Thank you. Oh, thank you. I don't deserve that today.